Hey everyone, my name is Jay and I'll be presenting Prim's algorithm. With that, let's get started. Okay, so Prim's algorithm. It's a greedy algorithm that finds a minimum spanning tree for a weighted, undirected graph. So it was first developed by a man named Wojtek Jarnik, but later it was rediscovered and republished by Prim and Dijkstra. Because of this, it goes by a couple different names. Sometimes it goes by Jarnik's algorithm, sometimes it goes by Prim and Dijkstra's algorithm, so that's worth noting. Something unique about Prim's algorithm is rather than building a subgraph one edge at a time, it builds a tree one vertex at a time, adding using the cheapest possible connections. So the time complexity depends on what implementation or data structure you're using. For a adjacent matrix implementation, it would be v squared, v being vertices, and for a binary heap or adjacency list, it would be v log v plus e log v, e being edges, v being vertices. Okay. So what's the importance of a minimum spanning tree? So there are lots of applications actually, but these are two. So the standard application is for a problem like phone network design. Let's say you have a business with offices in multiple places, and you want to lease phone lines to connect them up with each other. But the phone company charges different amounts of money depending on where you connect. So you want a set of lines that has a minimum total cost, and that's a good place to use a minimum spanning tree because it'll tell you the minimum cost, or help you find the minimum cost rather. And a less obvious application is to use it for the famous traveling salesman problem. There are a couple requirements that you have to check for with your graph before you actually use this algorithm. One is you cannot have self loops, meaning if you have a vertices, you can't have it have a edge to itself. And the second thing is you have to remove all parallel edges. So that means if you have two vertices, they can't have two edges between them. There can only be one edge per two vertices. And if there are two edges, you just go with one with the minimum cost, or lower cost rather. Okay, so this is Prim's minimum spanning tree algorithm. It's pretty simple. It might look like a lot, but if we go through like a visual demonstration, it'll make a lot more sense. And I'll show you that right now. So we start with the graph, a weighted, undirected graph, and we're going to pick a point to start at. It doesn't really matter what point we pick, but for this demonstration, I'll pick point 0, sorry. So we start at 0, and we notice that we have two paths. We're going to pick the path with the least amount of weight. So in this case, the path from 0 to 1 has a weight of 4. And the path from 0 to 7 has a weight of 8. So we're going to go down the path of 4. So we're going to connect 0 and 1. And now a new edge opens up because we get to 1. And that edge connects from 1 to 2. So we compare that edge with the edge from 0 to 7, and we see which one weighs more. So in this case, they weigh the same amount. And if they weigh the same amount, you can pick either. It doesn't matter. You should still get the same. You should get roughly the same cost graph. Okay, so we pick the bottom one, and a couple new paths or edges open up, and we're going to check the weight of these edges compared to the weight of the edge previous. So we're checking from 1 to 2, from 7 to 8, and to 7 to 6, and we're seeing which weight is the least. And we can see that the weight 1 by 6 is the least. So we're going to go from 7 to 6. And again, so we're going to check this weight, 8, against the weight 6. and against the weight 2, and we see that, you know, the weight 2 is the lowest. So we're going to go down from 6 to 5. And if you just repeat this step over and over again, you're eventually going to get a minimum spanning tree, just like this. And that's it. That's the basis of the algorithm. It's not too complicated, and basically you're just checking, you know, your previous edges and any new edges, and you're just you're just taking the greedy solution where you go with this lowest weight edge. It's not too complicated. Hope you guys learned something. With that,